Consider this situation. Suppose there is a particle moving along a circle of radius 2 meters and the particle is moving with a speed 5 meters per second. It's moving along the circle itself. That means its velocity is perpendicular to the position vector with respect to center. Okay. Can one of you tell me how much its angular velocity is? How much is the angular velocity of A relative to O? Do you remember any relation between speed of an object, radius of the circle, and angular velocity? We had used this many times in circular motion.
Sir, mv square by r.
Rishi, mv square by r is the formula for centripetal force. Okay, and that doesn't relate V, R, and omega.
Sir, V is equals to R omega.
Correct. V is equal to R omega. Fine. When an object is moving along a circle, its speed V, linear speed, is R multiplied with angular speed omega. Now, how do we derive that? Understand, like you have to keep the derivation in mind. We are discussing conceptual ideas. Suppose the object, okay, undergoes a small displacement from here to here. We know the object is following a curved path, but if you take a very small part of that curved path, it will almost be like a straight line. Okay, so the dl that I have shown here is the length of the arc along which this object is moving, small length, and that arc subtends a small angle d theta at the center. Now, how is length of an arc related to the angle subtended? Length is equal to r multiplied with angle in radians. So you can write dl is equal to r d theta and divide by dt on both sides. dl by dt is the speed v. So v becomes r multiplied with d theta by dt is rate of change of angular position. That is nothing but angular velocity. So you get v is equal to r omega. So remember, it is derived using dl is equal to r d theta. Okay, using the formula for length of arc in terms of radius and the angle subtended by it. Okay, keep this point in mind. You'll understand in the next problem why it matters. Okay, so v is equal to r omega. And now quickly tell me, how much is the omega of this particle?
2.5.
Omega is v divided by r. So 5 divided by 2, 2.5 radians per second. Okay, straightforward from circular motion. Okay. Next. Suppose there's a particle here moving with some velocity. Okay, let's assume its velocity is in this direction. Fine, maybe 20 meters per second. And consider a point somewhere here, which is at a distance, let's say 5 meters from it. This is the point O and this is the particle A, which is moving with a velocity 20 meters per second. Fine. Assume A is moving with a constant. Yeah, are you all able to see my screen?
Yes, sir.
Okay. Assume the particle A is moving with a constant velocity 20 meters per second as shown. Tell me, does this particle have any rotational motion with respect to O? Does this particle have any rotational motion around O or with respect to O?
No, sir.
Okay, Rishi, why do you say no? Because it's moving in a straight line.
No, because it's moving away from it and it's not The path is not around the point
Okay,
O also.
okay, okay. That's what. Depending on the path you are saying. Fine. Pawan, what do you say? Does A have any rotational motion about O or not?
Yes, sir.
How do you justify that?
There are 20 components తీసుకున్నామంటే అప్పుడు ఒక
Good.
కాంపోనెంట్ దానికి హెల్ప్ చేస్తారు కదా సార్.
Okay, okay, good, good. See, imagine this particle moving ahead along this path itself. It's going in the direction of its velocity. Any object moves in the direction of its velocity itself. So imagine its position after a small amount of time. Initial position vector you can see there. After a small amount of time, the position of the particle as observed from O will be like this. Okay. After some more time, maybe when the particle reaches somewhere here, the position of the particle as observed from O will be like this. So, Rishi, you tell me now, do you think the observer O will have to look in different directions to keep looking at A or not from time to time?
Yes, sir.
Yes. Okay. So even though A is moving in a straight line, it does have some rotational motion around O. Okay. And what Pawan was saying was correct. You can resolve the velocity into two components and tell at what rate it is rotating also. So that is the question now. You are given the distance. You are given the velocity with which the particle A is moving. You have to find out its angular velocity. See, you know that to keep track of A, the observer will have to change the direction of motion. Like the observer will have to look in different directions to keep track of that moving object. Okay. So there is a rate of rotation for that object. You have to find out the rate of rotation of the position vector. So calculate angular velocity of A with respect to O. Solve this quickly. And to find that out exactly, you need this angle. Take this angle as 37 degrees. Okay. So A is moving on a straight line at a particular instant. This is the situation. And you know, for the observer to keep looking at A, the observer needs to rotate their line of view. So that rate of rotation is what I'm asking you to calculate. Okay, listen all of you. We need angular velocity. Okay. By definition, angular velocity is rate of change of the angular position with respect to time. Okay. So let's consider a small interval dt. So in a small amount of time dt, the particle moves from this position to the next position. Actually, we have to take the immediate next position, but for us to be able to visualize, I'm taking a position which is slightly ahead. Okay. Imagine the position vector at that instant. At that instant, the position vector is like this. Okay. So this angle that you see here is the small angle that it rotates in a time dt. Fine. So we need that angle divided by time, but you don't know how much angle it is. All you know is its speed. So what you can do is, see, since the time dt is a very small interval, the angle d theta also will be very small. Then what you can do is you can imagine a circle here. The particle is not actually moving along a circle, but you can imagine a circle like this with O as its center. Fine. Now this angle d theta can be expressed in terms of this small arc length dl. Okay, let's call the length of this small arc as dl. And how are dl and d theta related? Like, you know the relation between length of an arc and the angle subtended by it. So you can write dl is equal to radius multiplied with angle subtended d theta. dl is equal to r d theta. Is it clear till this point? We have not solved the problem yet, but this is how we are going to do it. Rishi, did you understand?
Yes, sir.
Okay. Vanilla, is it clear?
Yes, sir.
Fine. Now we need to write an expression for that dl in terms of what is given in this problem. Now what is given in this problem? We know the speed with which the object is moving. Let's call the speed as v. Now dl, as you can see, is not in the same direction as the velocity. In fact, dl is in a direction perpendicular to the position vector 5 meters. So you have to take the velocity component in this direction. In which direction? We have to take the component of velocity 20 meter per second in a direction perpendicular to the radius 5 meters or the position vector 5 meters. Why should we take it perpendicular? Because the circle is always perpendicular to the radius. Fine. Now, what is the component of 20 in that direction? It will be 20 sine 37. 20 into 3 by 5, 12 units. So V perpendicular is 12 meters per second. Now, why are we bothered about that speed? If you know the speed in that direction, you can express the distance traveled in that direction. If that speed is 12 meters per second, then you can write the length or the distance traveled in that direction as that speed multiplied with time.
Sir, can you explain how you got V perpendicular as 12 meter per second again?
How much is the velocity?
20 meter per second.
Okay. What angle does it make with the what angle does it make with the circle?
D theta.
D theta is somewhere else. I am asking you about this angle.
Oh,
Angle
37.
No, 37 is not with the
Oh,
circle. 53 is with the circle.
53.
So its component becomes 20 cos 53. Cos 53 is 3 by 5.
Oh, yeah, sir, understood.
Okay, so that's how it becomes 12. Now with that component V perpendicular, we can express the small distance it travels in that direction. dl, distance, is equal to speed V perpendicular multiplied with time dt. Distance is speed into time. Good. Then we can write, okay, you can equate this to r d theta now. And what are you looking for? You are looking for d theta by dt, angular velocity omega, right? And that will be nothing but like send dt that side and r this side. You get it as v perpendicular divided by the radius r. V perpendicular is 12 divided by radius is 5. So that's 2.4 radians per second. So let's go through this once again. You were given an object which is moving along a straight line with a particular velocity of 20 meters per second. And at a particular instant, an observer is looking at that object. Now to continue looking at that object, as the object moves, the observer's line of sight has to keep rotating. Okay, so even though the object is moving in a straight line, we can say it executes rotational motion about this observer or with respect to this observer. Fine. And you were asked to find out the rate of rotation, which is d theta by dt or omega. Okay, so we visualized. Fine. As the object goes to the next position, we drew the position vector at the next instant. And we see that the original position vector, which is the orange one, and the new position vector at the next instant, the yellow one, have a small angle between them. Fine. The rate of change of that angle is what we want. So that angle divided by time is what we want. But we don't know the angle. So to find out that angle, we are using L is equal to r theta or dl is equal to r into d theta, where dl is the small distance traveled along the circle. So we imagined a circle. Now to travel along that circle, this complete velocity does not help. Only its component helps. Okay, so we took its component in that direction, which was 12 meters per second. Or we can call it v perpendicular. What is it perpendicular to? The radius vector or the position vector at that instant with respect to the center. Okay, so that perpendicular component is what helps in, or it is what results in rotation of that object around the center. Okay, and then omega is d theta by dt. If you do that, you get it as v perpendicular divided by r. So effectively what we are doing is we are using v is equal to r omega. We know that in circular motion v is r omega. Okay, but in circular motion this speed or this velocity is completely tangential. There's no radial component at all. Here this particle is not actually executing circular motion. It's going on a straight line. It's going on a straight line like this. Fine. But if you want to find out its rate of rotation, take the v perpendicular component and then put it in v is equal to r omega. So you better remember this equation as v perpendicular is equal to r omega. That's the relation between linear speed and angular speed of an object. Okay, and v perpendicular is the component of velocity perpendicular to the radius vector or the position vector. Fine. So basically what I wanted you all to understand that even an object moving in a straight line can have rotational motion depending on the observer. Okay. Next, let us discuss the quantity that we are supposed to, angular momentum of an object. Very important. Okay. Like it's one of the fundamental quantities in physics. And see, in physics, there are 4 fundamental laws which any system obeys. Okay. First is law of conservation of energy. Next is law of conservation of linear momentum, which we had discussed in laws of motion. If net force is 0, linear momentum is conserved. The third one is law of conservation of angular momentum. Okay. So conservation of angular momentum is something fundamental that happens in nature, and you need to know how to calculate angular momentum. And like if you want to talk about exams also, in every exam that you are going to take, final exam, you will definitely have questions based on angular momentum. Okay. Right. So let's understand what this is. Can any of you tell me the meaning of momentum? Like we had already discussed linear momentum. What do you understand from momentum of an object?
Mass into velocity, sir.
Abba. See, that is a formula. Okay, but I'm looking for the meaning of momentum. Suppose I tell you that there are 2 objects A and B, and the linear momentum of object A is greater than the linear momentum of B. What can you tell about the objects or anything?
But that means it's like it keeps increasing more than A,
What keeps increasing more than?
like whatever we're comparing.
No. When you just say one particular object has more momentum than another object, what does that mean?
Like it's gaining speed more faster.
See, if it has more momentum, doesn't mean it is gaining speed. Okay. Suppose there is a 2 kg object moving with 20 meters per second, constant velocity. Then its linear momentum is how much? 2 into 20, 40 kg meter per second. Fine. So it doesn't mean its speed is increasing. Like you can imagine another object, some 1 kg object moving with say 30 meters per second. Its linear momentum is only 30 kg meter per second. Doesn't mean A's velocity is increasing. No. In fact, it is moving slower and it keeps moving slower.
Sir, more momentum means it is harder to stop.
Correct. Okay. That is what I was looking for. That is the meaning of momentum actually. Momentum of an object is nothing but its tendency to continue in the state of motion. We had discussed this in laws of motion also. Mass is a measure of inertia of rest. Okay. Whereas momentum, okay, linear momentum is a measure of inertia of motion. What does inertia mean? The tendency of a system to continue doing what it is doing. Okay. Or the inertia tells you how difficult it is to change the state of motion of a system or rest of a system. Okay. So that is what is momentum basically. How much tendency it has to continue doing what it is doing, or another way to look at it is how much or how difficult it is to stop the object. That is what is momentum. Okay, hope this is clear to all of you. Now we had discussed linear momentum. When an object of mass m moves with a velocity v, then its linear momentum p is equal to mv. That's okay. Now, as the name suggests, angular momentum is nothing but rotational momentum of an object or a system. Means how much tendency a system has to continue its rotational motion. Or another way to think of it would be how much tendency a system has, sorry, not tendency, how difficult it is to stop the rotational motion of a system. That is what is its angular momentum. Okay, so you can say that angular momentum is a measure of rotational inertia. Fine, when it is actually rotating, measure of its rotational inertia is what is angular momentum. If it is at rest, then the measure of its rotational inertia is moment of inertia, the quantity that we had discussed in the last few classes. Okay, so moment of inertia and mass are analogous. They are inertia of rest. One is inertia of rest for translation, the other is inertia of rest for rotation. Linear momentum and angular momentum are analogous. Linear momentum tells you how difficult it is to stop an object executing linear motion. Angular momentum tells you how difficult it is to stop an object executing angular motion or rotational motion. Okay. Now let's see how this can be, how it is calculated. The symbol for angular momentum is L, capital L, and it's a vector quantity. Linear momentum is a vector, angular momentum is also a vector. Okay. So first, angular momentum of a particle about a point. About means with respect to, okay, a point. Consider a particle A, assume its mass is m, and let's say it is moving with a velocity v in this direction. Okay. First, consider a point O here, or yeah, let's consider this, let's call this point as P. Now you can visualize the position vector of A with respect to P. As observed by P, this is the position vector of A. Position vector of one point with respect to another is nothing but the vector connecting those 2 points. Fine. Now you all tell me, if A moves to the next position along this direction, okay, due to its velocity, it will shift to the next position. Actually, the next position has to be the adjacent position. But for us to visualize clearly, I have shown a position significantly further ahead. Let it be. Suppose A moves to that new position. Will the position vector of A with respect to P rotate or not? The position vector of A with respect to P, this new position vector, is it rotated compared to the earlier position vector, or does it have the same orientation, same angle?
Same orientation.
It has the same direction, same orientation. What does this mean? This means A, the particle A, does not have or execute. Okay, let's write execute. A does not execute rotational motion about P, means around P. Is this clear to all of you? Object is moving, it's moving in a straight line, and as seen by this observer P, it doesn't appear to rotate at all. Let's consider another observer somewhere here, Q. With respect to Q, this is the initial position of A at one instant, and at a later instant, as A continues to move forward, this is the position of A. Now clearly as A moves, A is moving on a straight line itself. Let it move. Okay. As A moves, for Q to keep looking at A, Q needs to change his or her direction of view. Fine. So A executes rotational motion about Q. Okay. And see, as A is moving on that straight line, for Q to keep looking at A, Q has to rotate his or her angle of sight, okay, or line of sight in the clockwise sense. So A has clockwise angular momentum or clockwise rotational motion with respect to Q. Hope this is clear to all of you. If you have any doubts, you can ask. Rishi, is this clear?
Yes, sir.
Vanilla, you understood?
Yes, sir.
Okay. Pawan?
Yes, sir.
Okay. Yusuf, you just joined, so I'm not asking you. But if you have doubts, you can ask. Next, consider another observer R. With respect to R, this is the initial position of A, okay, at the initial instant. Later, when A moves ahead, this is the position of A with respect to R. Clearly, as observed by the person R also, to keep looking at A, or with respect to R also, to keep looking at A, they need to rotate their line of sight. Okay, so A is executing rotational motion about R, okay, with respect to R. And that rotational motion about R is anti-clockwise. Fine. So an object moving in a particular manner can appear to be rotating in different ways for different observers. Fine. Therefore, to express the angular momentum of an object, you have to know with respect to which observer or with respect to which point you are calculating it. Angular momentum of a particle can change depending on the observer. That is what I want you to understand first. With respect to some observers, it may not have any angular momentum, any rotational motion at all. With respect to some observers, it may have a clockwise angular momentum, clockwise rotational motion. With respect to some others, it may have anti-clockwise angular momentum. Okay. Let's consider the observer Q. Just an example that I am taking. Okay, you can consider any observer. Now, with respect to Q, this is how the particle is moving. Particle has a velocity v, its mass is m. Assume this distance is r, or the position vector is r bar. Okay. Now you can resolve this velocity into two components. One component in the same direction as r, you can call it as v parallel. And you can take one component of velocity perpendicular to the position vector r, call it v perpendicular. One of you quickly tell me which of these components of velocity causes rotational motion of the particle, v parallel or v perpendicular or the complete velocity v. Which of these components results in the particle rotating around Q?
V perpendicular.
V perpendicular. That's what we had discussed in the last problem also. Okay, object may have velocity in any direction, but the component of velocity perpendicular to the position vector is what makes it rotate around this observer. Okay, so same thing here. So rotational motion depends on V perpendicular. So obviously angular momentum should depend on V perpendicular. So that's one factor on which it depends. And when it comes to momentum, you know that heavier objects are difficult to stop, lighter objects are easy to stop. So momentum, anyway, whether it is linear momentum or angular momentum, it should depend on mass of the particle. That is another factor on which it depends. The third factor on which angular momentum of this particle depends is the distance at which it is from the observer. Okay, this you can say has been determined experimentally. If an object is moving with a particular speed close to an observer, it is easy to stop. If it is moving far, like its rotational motion is easy to stop. Okay, and if it is moving far from an observer with the same speed, its rotational motion is more difficult to stop. Okay, it is found to have more tendency to continue its state of motion. So angular momentum L depends on these three factors. There is m, there is the distance r, and there is the component of velocity perpendicular to that position vector, which is v perpendicular. It depends on these three. Fine. And by definition, the magnitude of this quantity called angular momentum is directly the product of these three, m, r, v perpendicular. That is how you calculate magnitude of angular momentum. Mass of the particle, distance of the particle with respect to the reference, multiplied with component of particle's velocity perpendicular to the position vector. Okay. But as I said, angular momentum is a vector quantity. It has direction. And in this case, understand the direction. If object continues to move along this path, you know that its position vector is rotating clockwise. With respect to q, the position vector of this particle is rotating clockwise. Therefore, its angular momentum is clockwise. Basically, its rotational motion is in the clockwise sense. That is what we mean. Okay, so angular momentum is a vector quantity. Fine. Observe the factors on which angular momentum depends. Mass. Mass is a scalar. You can do nothing about it. Let it be as it is. What is r? R is the magnitude of position vector. Okay, I'll write it here. Magnitude of r bar. And perpendicular velocity. That's component of velocity perpendicular to the position vector. Now in the angular momentum formula also, mass is written as it is, but r and v perpendicular are multiplied. Okay. R is the magnitude of one vector. V perpendicular is the component of second vector in the direction perpendicular to the first vector. You can see that, no? V perpendicular is the component of velocity perpendicular to r. Now you all tell me which operation between two vectors, okay? Which operation between r vector and v vector gives you this product, r multiplied with v perpendicular? Should you add them? Should you subtract them? Should you take dot product or should you take cross product?
Cross products.
Those are all that we learnt about operations between vectors: addition, subtraction, dot product, cross product. Addition, subtraction won't give you the product r into v perpendicular. Dot product gives you r multiplied with v parallel. Cross product gives you r multiplied with v perpendicular. Okay, I'm sure you all revised this. So if you take r cross v, its magnitude becomes rv perpendicular. And that is what we want to express the angular momentum of a particle. So this is how cross product matters for angular momentum calculation. Okay. So the magnitude of cross product between r vector and v vector gives you r multiplied with v perpendicular. That gives you the magnitude of angular momentum. But angular momentum has a direction also. Let's see if the cross product can give us the direction as well. Now to get r v perpendicular, you can take magnitude of r cross v. You can even take magnitude of v cross r. Which one exactly to take? Which one should actually be considered? Let's see. Now you all can see the r vector and v vector here. If you want, I'll draw them again. The r vector and v vector are seen directly here. From your knowledge of cross product, you all tell me what is the direction of r cross v and what is the direction of v cross r. Both you tell. Okay, type your answers in chat. Okay, I got two answers as first clockwise and second anti-clockwise. They're correct. See, to get the direction of cross product r cross v, you should imagine moving along the first vector r and turning in the direction of second vector v. So what sense of rotation is this? Clockwise? Fine. If you want v cross r, you should move in the direction of v first and then turn towards the direction of r. This way, and the red arrow, it gives you a sense of anti-clockwise rotation. Fine. Now the angular momentum of this particle as observed by Q is clockwise. Fine. Therefore, to get angular momentum along with direction, you should take r cross v, not v cross r. Okay, so this is what we are going to use. Now let's get back to angular momentum. Angular momentum magnitude was m times r multiplied with v perpendicular. Now to get r multiplied with v perpendicular, you have to take cross product between r vector and v vector. Whether to take r cross v or v cross r is what we just confirmed. You have to consider r cross v. Therefore, angular momentum as a vector along with direction can be calculated this way. Keep mass aside, it's a scalar quantity. Then you take cross product of r and v. So m r cross v is the proper formula for angular momentum of a particle about some point. M is the mass of the particle, r is its position vector, v is its velocity vector. When you take cross product between position and velocity, the cross product ensures that you are multiplying r with v perpendicular. So automatically the perpendicular component only will be considered. Complete velocity won't be considered. Okay, is this clear to all of you? Why the formula for angular momentum is mr cross v?
Yes.
Okay. Now you can calculate it in another way also. See, the magnitude of r cross v is r multiplied with v perpendicular, which is nothing but r v sine theta. It's like ab sine theta. You can also take it as v multiplied with r perpendicular, nothing wrong in that. So v multiplied with r sine theta also can be taken. How do you do that? Understand this point is very important. When we solved the problem for angular velocity, okay, we kept the position vector as it is. We kept the radius as 5 meters and we took component of velocity perpendicular to the radius. Okay, so we took r as it is and we multiplied and we used v perpendicular to get omega. That makes sense. That is fine. There is another way also to calculate angular velocity, okay, or angular momentum. How you can do it is, consider this same situation. You can visualize the r vector. You can visualize the v vector that is given to you. This time we won't take v perpendicular. We will take v vector as it is and take r perpendicular. Okay. Now what is r perpendicular? Component of r perpendicular to velocity. So what you have to do is visualize this line. What is this line? Line of action of velocity of the particle. Okay. And how do you take r perpendicular? You have to take the component of r perpendicular to that line. And that will be this distance. So the original vector is r. Its component perpendicular to the line of action of velocity is r perpendicular. So the distance from here to here is what matters. So angular momentum can also be calculated as m v multiplied with r perpendicular, magnitude wise. Direction, you can't do anything about it. Whether you multiply v with r perpendicular or r with v perpendicular, direction is clockwise only. That you cannot change. Okay, but magnitude calculation, whichever way you are comfortable, you can proceed. Now remember, r perpendicular is the perpendicular distance from the observer or reference to what? To the line of action of velocity. Fine. So to calculate angular momentum of a particle about a particular observer or with respect to a particular observer, you can keep its velocity as it is and multiply with this perpendicular distance also. So let's summarize all this. The angular momentum of an object, of a particle actually, is the proper formula is m times r cross v. You are not supposed to change the order. You can't write it as v cross r. Okay, because we discussed in the last class, cross product discussion. R cross v and v cross r will be exactly opposite to each other. Okay, so order is very important. It is given by m r cross v. Mass, if you want, you can multiply that side. Like you can evaluate r cross v first and then multiply with mass. Mass is a scalar, so it doesn't matter whether you multiply it first or second. So this is the formula for angular momentum. Now, if you only want the magnitude of angular momentum, you have to do mrv sine theta, where theta is the angle between r and v. Or you can do mv multiplied with r perpendicular. You can also use mr multiplied with v perpendicular, any one of them, to find out the magnitude of angular momentum of a particle. Okay. Let's solve some problems based on all this. I want all of you to participate. Some of you are not responding at all. Okay. See whether it's right or wrong. Like you may have that doubt in your mind. What if I am wrong? So what, you learn, that's all. But if you have done solving, you should tell what you did or what answer you got, so that I can correct you if you are wrong. Suppose there is a particle of mass 2 kg moving with some velocity in this direction. Okay, it's moving parallel to the x-axis. How much velocity shall we give? 10 meters per second maybe. Okay. At a particular instant, at this moment, let's say it is at some position. Pawan, tell me some rough coordinates of this object. X coordinate, Y coordinate, chepo.
Sir, 5,6.
5,6. Okay, Y coordinate looks bigger than the X coordinate. So 5,6, fine. Konjam proportionality maintain cheyandi. Let's take it as 5,8. So the object is at this position 5,8 at this moment. It's a particle only. I should not call it an object actually. Okay, so you know its mass, you know how it is moving. I want you to calculate its angular momentum about the origin. Do this, all of you. Calculate angular momentum about origin. See, you know what you should visualize to derive angular momentum. You have to visualize the position vector r bar. You have to visualize velocity and you should know the mass. Okay. You can do all that based on the information that is given to you. And then you can use one of these formulas that are written on your screen to actually calculate the magnitude and direction. Okay, try. I'll give you all 2 minutes. Type your answers in chat and I want answers like this: a magnitude and direction, clockwise or anti-clockwise. That's all. Or if you want to give direction in terms of I cap, J cap, K cap, that also you can do. Try. Okay, I got one answer as 160 clockwise, the other as minus 160 K cap. Both are correct. Fine, listen. You are asked to calculate its angular momentum about the origin. Now, if you want to get it as a vector directly, you will have to use this formula m r cross v perpendicular, r cross v. Okay, mass is known to us. Visualize the r vector, the position vector. Yusuf, can you tell this vector in terms of I cap, J cap? The particle is at 5,8. So how do you express its position vector?
5 I cap and 8 J cap.
Correct. 5 I cap plus 8 J cap. And that will be in meters. Okay. So we have the r vector. Now, Pawan, can you tell me this velocity as a vector?
Sir, 10 I cap.
10 I cap. It is 10 meters per second in the positive x direction. So 10 I cap. That's all. We have all that we need. So angular momentum, mass 2 kg. We can multiply it later also. R cross V. R is 5 I cap plus 8 J cap cross. velocity is 10 I cap. That's all simple. Keep the 2 as it is. One of you tell me, what is 5 I cap cross 10 I cap?
0, sir.
0. And how much is 8 J cap cross 10 I cap? 8 tens is 80 and J cross I is minus K. That's all. Therefore, the answer is minus 160 K cap in SI units. Now, angular momentum is mass, mass, position vector and velocity multiplied. Multiply all of them. The unit will be kg meter square per second. Okay. So we got the vector as it is, minus 160 K cap directly. Now, there are other ways also to solve. You can express the magnitude first and then assign a direction. Now, actually, we got the answer already, but you get used to these other methods also. Fine. Let's try using MV R perpendicular. Fine. Now, if you want to get the magnitude, you can try MV R perpendicular. Its mass is 2 kg. Its speed is 10 meters per second. The only thing we need is R perpendicular. Can one of you tell me what R perpendicular means? From where to where should we take the distance R perpendicular?
Perpendicular distance between O and KG, sir.
Between O and
Particles.
see, O is a point, particle is also a point only. Between 2 points, there is no perpendicular distance. There is only a distance. Okay, keep this point in mind, all of you. R perpendicular is the perpendicular distance from the reference to the line of action of velocity. How the particle is moving is important. Now, in this question, the line of action of velocity is this. So, this becomes the perpendicular distance. Okay. Rishi, how much is that distance?
Sir, 8 units.
8 units, 8 meters. That's all. 2 into 80 is 160. We got the magnitude. And now we have to assign a direction to it. Now the particle is moving to the right side. As particle moves to the right, its position vector rotates this way. So what's the sense of rotation here? The sense of rotation is clockwise. Curl your right hand fingers clockwise. Your thumb will point, your right hand thumb will point into the screen. So you can express its angular momentum as 160 in the clockwise sense, or you can write it as minus K cap. So this is another way to derive it. So what did we do here? We derived the magnitude first, okay, and then we assigned a direction to it. Based on how it is moving, you can tell whether it is clockwise or anti-clockwise. Okay. There is also another method to find out angular momentum, MRV perpendicular. That will be difficult in this situation. Why will that be difficult? Let's see. If you want to use MRV perpendicular, you have to take the distance R first. That is one time taking thing. You have to take the magnitude of this, or you know the distance formula, no, root of x2 minus x1 whole square plus y2 minus y1 whole square. You can use that. You can get it, but it is time taking. The next thing is even more time taking. If you take R as it is, then you will have to take component of velocity perpendicular to R vector. That is a headache here. How will you get this component of velocity? You don't even know the angle between R and V. Okay. So getting V perpendicular will be difficult in this case. I'm not saying it is impossible, but it's difficult to do. Okay. So remember, there are 3 different ways to calculate angular momentum depending on the convenience. You can use MR cross V, write the vectors and take cross product. Otherwise, find out magnitude and then assign direction. To find out magnitude, there are two ways, MVR perpendicular or MRV perpendicular. Which of them is convenient, you have to decide based on the problem. Here, MVR perpendicular is very convenient to use. And we did that, we got the same answer. Okay. Try another problem. Suppose there's a particle here, and let's say it's moving in this direction. With a speed 40 meters per second. At what angle? 53 degrees with the x-axis. And you have to find out its angular momentum about the origin itself. And what are the coordinates of this particle? Say 10, 0. And I have to give you its mass. Assume mass is 3 kg. Okay. Derive angular momentum about the origin. Again, I'll write the 3 approaches that you can take. You can use L is m r cross v to get the angular momentum directly, or you can find out the magnitude first using mrv perpendicular or mvr perpendicular and then assign direction. Try. Okay, Vanilla, Aishwarya, your answers are correct. Pawan, how are you trying to solve this?
Sir, answer వచ్చింది. Type చేస్తా.
Okay. Yusuf, how are you trying to solve this? Okay, fine. It's better if you can unmute. Rishi, you tell me. Suppose you want to use mr cross v. In this particular situation, how much is the vector r?
10.
Vector, you have to tell in terms of I cap, J cap, K cap.
Oh, 10 I cap.
Okay, r vector is 10 I cap. Okay, fine. Can you express its velocity as a vector? Like this 40 meters per second, can you express it in component form?
Sir, 40 into sin 50.
What? 40 into sine 53. And what component is that? Perpendicular component.
Yes, sir.
Okay. No, I'm asking you for the complete vector. Anyway, fine. Let me explain this. So if you want to solve it using the first method, mr cross v, you will have to write this velocity in vector form. Let's do that. The velocity's y component will be 40 sine 53. 40 into 4 by 5. 40 by 5 is 8. 8 4 is 32. So 32 j cap. And its x component will be 40 cos 53. Cos 53 is 3 by 5. 8 3 is 24. But it's in the negative direction, so minus 24 I cap. Therefore, its velocity vector, if you want, it becomes minus 24 I cap plus 30, okay, 32 j cap. And then you can use mr cross v. Mass is 3 kg. R vector is 10 I cap cross v vector is minus 24 I cap plus 32 j cap. Now 10 I cap cross minus 24 I cap is 0. So 3 you multiply, you take as it is, 0. 10 I cap cross 32 j cap. 10 32 is 320. I cross j is k. That's all. 3 times 320 is 960 k cap. Kg meter per second. That is its, kg meter square per second. That is its angular momentum about the origin. Okay. But
Sir,
see,
1 second,
yeah.
sir.
Huh.
I got the same answer, but the way I did it, I think
Yeah,
was
I
bit
understand.
wrong.
I'll explain that. It's not wrong. You used these ideas. Okay. You took the perpendicular component and used it instead of taking the complete velocity. Nothing wrong in that. Now see, there are other ways also to derive the angular momentum. We'll find out magnitude, mrv perpendicular, and then assign a direction. If you want to use mrv perpendicular, you should know the mass. You should know the distance. In this problem, distance is directly known to you. R is 10 meters. V perpendicular is 32. So mass is 3 kg, distance is 10 meters, V perpendicular is 32. You can easily calculate. And the way this object is moving, clearly it is moving anti-clockwise. Curl your right hand fingers anti-clockwise, thumb will point outwards, means k cap. So 3 into 10, 30 into 32, 960 k cap. So you can calculate magnitude, assign a direction. Here we didn't use cross product. Okay. So if you're not comfortable using cross product, you can go for this method. If you try to do it the other way, the third method, MVR perpendicular, that will be complicated here. V is 40, okay. But taking R perpendicular distance will be lengthy. You'll have to use right angle triangle properties, like trigonometry and all. So in the previous problem, MVR perpendicular was easy. In this problem, MRV perpendicular is easy. So it all depends on the situation. Fine. So according to the question, whichever is convenient, whichever method is convenient, you'll have to go by that. Okay. So what have we discussed so far? We discussed how to calculate angular momentum of a single particle about a reference. Fine. Now I told you that the rotational motion of a particle with respect to a reference can change from reference to reference. With respect to some reference, there may not be any rotational motion at all. With respect to some reference, the rotational motion may be clockwise. With respect to some other reference, it may be anti-clockwise. Okay. So angular momentum, which is basically inertia of rotational motion, will definitely depend on the observer or the reference. So angular momentum depends on the reference. So whenever you are asked to calculate angular momentum, no, you will also be given about which reference you are asked to calculate. Fine. The basic formula we discussed, and we even discussed why there is cross product involved in angular momentum calculation. See, this is what I was telling you in the last lecture when I taught you cross product. Cross product is an operation we define between two vectors to get the result the way we want. To express this quantity angular momentum, cross product is useful. Taking like that operation between vectors is useful. In this chapter itself, going forward, maybe next class or the class after that, we'll discuss another quantity called torque. In torque calculation also, this cross product will be useful. And then we solved two problems where we calculated the angular momentum of a particle about a given reference in different ways. Okay, fine. So tomorrow I'll send you a worksheet based on angular momentum of a particle and cross product. You solve that worksheet, and Friday's class will continue. Today we only discussed angular momentum of a single particle. Next class we'll discuss how to express angular momentum of an entire system. Okay, and angular momentum of a system varies depending on how the system is moving. Obviously, it depends on how it is moving. But when I say how the system is moving, I mean what kind of motion it is executing. The formula itself will change. For translational motion, you will have one formula for angular momentum. Rotational motion, you will have another formula for angular momentum. Okay, so next class, what we are going to do is, we are going to use this basic formula. This is for a particle, no? That's what we discussed today. We will extend this to a system, and we will derive a final formula based on the kind of motion the system is executing. Okay, so let's just like what we do in center of mass, moment of inertia and all, we'll first learn how to calculate for a particle, then we'll extend that to a system. Fine, we'll stop it here. We'll continue in the next class. Thank you all. But tomorrow I'll be sending you a worksheet. Make sure you solve that.